The final topic for this week is on equilibrium of a three-body force. Consider the following bodies shown below subjected to three forces, A, B, and C. How large must force C be, and where must it be located if the body is to be in equilibrium? Note here that C is an unknown force with an unknown direction and distance. Let's draw our sign convention on our diagram so we know what direction is positive. Let's assume Cx and Cy goes in the positive x and y direction respectively. We can also draw AY, AX, BY, and BX. BY is negative according to our sign convention. First, we write and solve the governing equations. Using the equations of equilibrium, we can solve for Cx. The net force in the x direction equals 0, which equals Cx plus Ax plus Bx. Rearranging, you get Cx equals negative Ax subtract Bx. Using the equations of equilibrium, we can solve for Cy. The net force in the y direction equals 0, which equals Cy plus Ay subtract By. Rearranging, you get Cy equals negative Ay plus By. Next, we'll take the moments about point Q, which is where the lines of action of A and B intersect. Remember that the moment equation is force times perpendicular distance. We do not include forces A or B as they are in the line of action. The moment about Q must equal 0. That means the absolute value of C, as we are assuming the force of C is a non-zero number, times the distance must equal 0. That means that the distance must be 0. Now we can interpret the results, which tells us that the lines of action of the three force vectors must intersect at a common point. The relationship where all forces must intersect at a common point is called the principle of concurrent forces, and it only applies when there are either two or three forces acting on a body. Note that although the line of action of force C must pass through Q, the force C does not need to be applied at point Q. This principle does not apply when there are four or more forces acting on a body. It also does not apply when all the forces are in the same direction. The reason is because parallel forces will never intersect. Even though these forces shown below are different lengths that indicate different amounts of forces, they are parallel and will never intersect. It's also known as having an intersection of infinite distance. Let's try an example. A ladder leans against a frictionless wall as shown below. Find the reactions at the ends of the ladder when a 200-pound person is halfway up the ladder. Assume that the contact between the ladder and the wall is frictionless. Note that the distance from the base of the ladder to the wall is 5 feet and the height of the ladder is 20 feet. Feel free to pause the video and try this problem on your own. Let's start by labeling this point A, this point B, as well as the weight can be labeled as W. There are several methods to solve this problem, but we'll solve it using the principle of concurrent forces. Since this ladder is a three-force member, based on the principle of concurrent forces, the forces must intersect at a point. In this case, a point that is off the ladder. First, let's redraw the diagram. Start by drawing your sign convention. Then draw the wall, base, ladder, points, and distances. We're assuming the base and wall meet at 90 degrees as well. When adding the distances, don't forget that the weight is halfway up the ladder. Let's draw our respective forces, AX, AY, W, and BX. Notice how there's no BY. That's because we're assuming no friction occurs from the ladder and wall, so it doesn't give us a BY force. If we draw the lines of action of W and Bx, we can see that in order for the principle of concurrent forces to be true, the line of action of A must intersect with the lines of actions of W and Bx. We can see that the forces will intersect at 20 feet somewhere in the line of action of W. This slide just shows the cleaned up version of our diagram, split in half with forces and distances. We can move BX to the bottom since we're creating a force triangle, tip to tail, assuming the system is in equilibrium. Now that we have our diagram, we can use this information to solve for AY using equilibrium equations. Notice how the only vertical component of this diagram is the weight, which equals 200 pounds. That means that the net force of Y would equal 0 in equilibrium, which is equal to AY subtract W, since it's in the negative Y direction, according to our sign convention. With W equaling 200 pounds, that gives us AY equals 200 pounds. Notice how the force moves 2.5 feet to the right and 20 feet upwards to reach the common intersection. Based on the force to distance ratio of the system, we can now find AX. So AX over AY equals 2.5 feet over 20 feet. Remember that AY equals 200 pounds, which gives us AX equals 25 pounds to the right. Finally, we can find BX using equilibrium equations. The net force in the x direction is equal to 0, which is equal to AX subtract BX as it's in the negative direction, according to our sign convention. Remember that AX equals 25 pounds, which gives us BX equals 25 pounds to the left. This slide shows the final diagram with all the forces and distances. To double check that your answers are correct, take the moment about point A. You should get 0. Feel free to pause the video and try it on your own. Using the moment equation, you get the moment about A equals 0, which equals positive BX as it's counterclockwise, times 20 feet, plus negative W as it's clockwise, times 2.5 feet. This gives you 0 equals 25 pounds times 20 feet, plus negative 200 pounds times 2.5 feet. This gives you 0 equals 0, meaning our answer is correct. A ladder may fail because the base is slipping away from the wall, the top is tipping away from the wall, or the rails of the ladder fails in bending. For what position of a person along the height of a ladder is each mode of failure more likely? Pause the video to try it on your own. Base sliding will occur when the person is at the top. This is because the horizontal force will be pushing the bottom of the ladder to the left, whereas the horizontal force at the top will be pushing the top of the ladder to the right. This is the result, as you can see the ladder has slipped down. Tipping will occur when the person is at the bottom. This is the opposite of base sliding, as the horizontal force at the bottom will be pushing the bottom of the ladder to the right, and the horizontal force at the top will be pushing the top of the ladder to the left. This is the result, as you can see the ladder is falling backwards. Bending will occur when the person is in the middle. This is because all the weight will be directly in the middle of the ladder, causing it to bend in half. This is the result, as you can see the ladder has started to bend. In summary, the principle of concurrent forces only applies when there are 2 or 3 forces acting on a body. It does not apply when there are 4 or more forces acting on a body, or all the forces are in the same direction. The steps we took to solve the leaning ladder problem were finding the forces that were acting on the body and the approximation of where the forces will intersect. Don't forget to account for distances and friction. Solve for AY and BX using equilibrium equations. Solve for AX using similar triangle ratios. The last thing was to double check your answer by taking the moment about point A and making sure you get an answer of 0.